Hello, we are on our second of two videos, so it's not very many objectives in this section 6.6, and we're going to be solving exponential equations. All right? So let's begin with looking at two exponential equations. I want you to recall that if you have a to the u equals a to the v, then u equals v. Why is that true? Well, these are exponential functions, right? Are exponential functions one-to-one? Yes, they are. They can go up like this. So they pass the horizontal line test. So u must equal v. So a lot of people try to dumb it down a little bit and say, oh, okay, that's true. Then you just drop off the bases. It's a weird way of thinking about it, and although it is true, and you won't make a mistake if you think of it that way, it's not what the problem is really saying. It's because it's one-to-one. So you're not applying an operation to get rid of the bases. So when you say get rid of the bases, you're really saying I need to apply some operation to get rid of them. You are applying the idea that exponential functions are one-to-one. So that's why the bases are gone. So if a to the u equals a to the v, then u equals v. The reason behind it is however you want to do it. You just got to remember that this is what it is. Okay? So let's look at an example. Now, look at this one. If you have 5 to the x plus 3 equal to 3 to the 2x minus 5, do you see how the problem's ratcheted it up in difficulty? Look at the bases are different. So base is 5 on one side and base 3 is on the other side. All right? So we need to solve that equation. You can't just set the bases the same because base 5 and base 3 cannot be made the same. The only way you make bases the same is reduce the numbers. You might think, well, you can change them to both base 15. No, you can't, because you can't change 5 to the x plus 3 to base 15. Well, at least very easily you can't. Okay? So 5 to the x plus 3 and 3 to the 2x minus 5, guess what we get to do? We have to invoke logarithms here. Okay? So let's look at this. Let's look at this solution. Because the bases are different, we need to first apply property 7. Now remember what property 7 is. Property 7 stated if u equals v, then log base a of u equals the log base a of v. Base a could be anything. Okay? So this time we're going to take the natural log of both sides, each side. And then use the properties of logarithms to finish it up. And the result of the equation is in x that can be solved. So this is how you solve these types of problems. So if you really wanted to know, why do we do logarithms? Why is that such a big deal? Okay? This is the grand reason, okay, for this, at least for this course, is if you have 5 to the x plus 3 equal 3 to the 2x minus 5, without logarithms, you are done. You can't solve this problem. You need logarithms to do it. So what we're going to do is take the log on both sides. Now that log can have base b, base 5, base 7, base 10, or base e. I'm going to use base e, which is natural log, because it's more compact. 2 letters at the max, so the ln on both sides. So you're going to see me have it right. When I solve this problem, when we're done, I want you to count the number of times I wrote the natural logarithm. If you use anything else like a common log, you'd have to write that same number of times. Okay? And you wouldn't even want to use a base 5 or a base 7 because you can't even calculate those without the change of base theorem. We want to use something that we can use the calculator with, so that's why we either use common log or natural log. Although we can use any base we like, common log and natural log are our friends. Okay? ln is the best friend because it's got one less letter as opposed to a common log, log. Okay? So let's look at this. All right? All right, so we've got 5 to the x plus 3 equal 3 to the 2x minus 5. So we take the natural log of both sides. So you have the first equation changes to the second equation. All I did was I applied an ln. And the reason I can do that is because it's one-to-one. If m equals n, then the natural log of m equals the natural log of n. Then I'm going to take the x plus 3, the exponent, and write it as a factor. And then I'm going to take the 2x minus 5 on the right side and write it as a factor. Why can I do that? Because of the power rule of logarithms. And you're like, first of all, why would you want to do that? You can't solve for x as long as it's written in the exponent in these problems. But you can solve it if they're factors, because we know the inverse operation of factors. We know at some point we're going to be dividing. So when x comes down into the factored form, okay, then it can be solved by distributing and things like that with, day-to-day operations that we've learned. So that's why we do logarithms, so when we put logarithm on both sides, we can use the power law to bring it down as a factor. Once it comes down as a factor, it's basic operations. It's in the intermediate algebra student can go from there. But an intermediate algebra student would not know what logarithms are all about. You do. Okay, now, so what you do is you take those exponents and you write them down as factors. Then you take the natural log of 5 and distribute that through the parentheses. So you have x times the natural log of 5 and 3 times the natural log of 5 on the left side. On the right side, it's natural log of 3 times 2x. And then the natural log of 3 times the negative 5. So it'll be negative 5 natural log of 3. So you distribute. Okay? So now it's just about manipulation. Okay, look at you got 4 terms in that equation total. 2 of those 4 terms has an x in it. The first one and the third one. The second term and the fourth term do not have x's. So we need to isolate the x. So what we need to do is bring the x's on the left side and what I call the non-variable terms, like the 3 natural log of 5 and the 5 natural log of 3, put them on the right side. So basically we segregate them. To segregate the x's on one side, and we segregate the non-x's on the other side. So we got natural log of 5 times x minus 2 natural log of 3 times x equals negative 5 natural log of 3 minus 3 natural log of 5. So we put 1 on one side. So we put terms involving x on the left. The ones that do not have x, put those on the right. And then here's the key. You factor out the x on the left side. They both have an x factored out. Now how could I isolate that variable? We've got a big growth on the left side, don't we? We have a natural log of 5 minus 2 natural log of 3 attached to the x. We've got that's what I call a growth. How do you get rid of the growth? You divide it to the other side. So x equals the negative natural log of 5 times 3 minus 3 times the natural log of 5 over the natural log of 5 minus 2 times the natural log of 3. That is the exact solution. And I will be asking you for the exact solution. But I also want the approximated answer. So look at the final answer. X is 17.56. Where does that come from? That comes from the evaluation of the expression above it. So you got to know how to put these numbers into a calculator. So you would take the numerator, put that in parentheses. So you have parentheses, negative 5, ln 3, minus 3, ln 5. Close that parentheses off. Divided by, open up another parentheses, and put natural log of 5 minus 2 natural log of 3 on the bottom, and close it off. Every individual logarithm that you have, you'll probably have to put parentheses around that one as well. Because once you hit ln, most calculators will open up parentheses for you automatically, so then you need to close it off immediately. So everybody's calculator is different. I can't sit here and tell you how to use everybody's calculator. That would take too much time. When in doubt, pull out your manual and figure that out. So it's 17.56 is the approximated answer. Now I want you to understand what this is about. That means if you take approximately 17.56 approximately and put that back into the original problem for x. So if you take 5 to the 17.56 plus 3 and then take 3 to the 2 times 17.56 minus 5. Evaluate the left, evaluate the right. I don't know what they are, but I will tell you one thing. They're about the same thing. And you're like, why aren't they exactly the same thing? Because it's an approximated answer. 17.56 is approximate. If you go out further than 17.56 out to say, let's say 8 to 10 decimal places, which would be very hard to check, by the way, those numbers would be really close together, if not the same. Okay? So the more you go out, the closer the left side and the right side of the original equation are going to be. All right? So, but 2 decimals is usually what they'll be asking you for in my math lab. I might ask you to go out to 3 decimal places on your calculator, but that's no big deal. Okay? But one thing before we move on, I want to show you guys something. Count the number, in our solution, count the number of times LN was written down. I'm counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I am counting 20 times that in my solution that I had to write LN. Now, if you chose to use LOG, no problem. You could. But you're going to be writing that LOG 20 times as well. Okay? So, whichever you choose to use, be consistent. You can't mix and match them. Either write LN every time, which is what this problem is doing, or LOG 20 times, which is what you could do if you wanted to. Log base 5 or log base 7 or log base 9, those numbers could be used as well. The only problem with that is when you try to go from exact to approximated solution, you're going to have to invoke the change of base theorem several times. So if you try that, but you're going to only try it once because you're going to get fed up with that. So, LN is your best friend. LOG is a friend as well, but when you're trying to solve these problems, don't go to a different base. Otherwise, when you get to the final answer, from exact to approximated solutions, you're going to cause yourself a little grief if you tried it that way. Okay? So, all right. So let's move on. Let's look at a different example. So solving the exponential equation that is in quadratic form. These are the ones that cause students the most grief. Okay? It's you got exponentials, but they're in quadratic form. If you take 4 to the x and look at that one, that's 2 to the 2x. So you could solve that equation if you take it 2 to the 2x minus 2 to the x minus 12 equals 0. Now factor as usual. Okay, so 2 to the x minus 4 times 2 to the x plus 3 equals 0. So 2 to the x equals 4, and 2 to the x equals negative 3. Now, 2 to the x equals negative 3, can't solve that, right? Because exponentials cannot equal negative 3, negative numbers at all. So that whatever that comes out there is going to be extraneous. But 2 to the x equals 4, what does x have to be? X has to be 2. 2 squared is 4. All right? Now, so the answer is 2. Now, I'll give you an easy one to look at just to give you some ideas, okay? But here's the trouble, guys. Some of these problems that's in quadratic form can be written with different bases. So instead of having 2 to the x equals 4, you could end up with 2 to the x equals 7 if it factored a different way. Instead of having 2x to 4, you have 2 to the x equals 7. What happens in that case? You have to apply a previous technique. If you have 2 to the x equals 7 instead of 2 to the x equals 4, what would you do? Yep, you would take the natural log of both sides. So, and then that brings the x down as a factor. So if you can't solve x easily because the bases are different, then you must take the natural log of both sides. So the exponent, the variable which is in the exponent's position, needs to come down. The only way that's going to happen is if you take the natural log of both sides. So that's when you get to bring it down. But in this case, 2 to the x equals 4. I mean, can you do it the same way? Sure. You could take the natural log of 2 to the x equals natural log of 4. Then bring the x down. Then you have natural log of 4 divided by the natural log of 2. Natural log of 4 divided by the natural log of 2 turns out to be 2. So you get the same answer. So, but just be prepared when you get to some homework, and you won't end up with 2 to the x equals 4. You might end up with 3 to the x equals 5. So if you have 3 to the x equals 5, that's okay. You just take the natural log of both sides. That brings the x down, and so it becomes natural log of 5 divided by the natural log of 3. So that's where you got to be careful with. This one was a little easier problem because your 4 and your negative 3, well, the 4 is a power of 2, which is the base. A lot of times the answer, the factor, is not a factor of the base or a power of the base, but like this one was. Okay, so like I said, you could end up with like 3 to the x equals 5, and 5 is not a power with base 3. You can't get those the same. So that's when you got to take the natural log of both sides. Okay, so that concludes this video. If you want to see a video that has one a little bit more complicated, I try to streamline these so they won't be so long, and so you're not sitting there, waiting for these things to stream on your videos at home. So it makes it a little easier to watch them. Yeah, but sometimes there's examples that I'm not putting in there because of that, and just because of time constraints. Okay, but if you want to see one of those and that has a different base where you have to take the natural log of both sides, you be sure to email me and I'll send one out to you. Okay, so, and as always, you have a good day.